The world is just about to witness a tragic disaster. Millions across the globe have tuned in to watch the first participant of the Teacher in Space programme ascend into space. Excitement is building as the Challenger Space Shuttle is just moments away from launch. The time is 11:38 AM and it's the 28th of January 1986. The shuttle is just about to lift off the launch pad at Kennedy Space Center, and although initially off to an apparently good start, just 36 seconds later the craft is hit by a strong wind shear. Not long after, a small plume of smoke is seen. At 60 seconds post-launch, Capcom informs Challenger to go at throttle up. Just 5 seconds later, the Challenger began disintegrating, and quickly after, a fireball consumed the shuttle stack. The world had just witnessed the loss of one of NASA's cutting edge in human space travel. Today we're looking at the Challenger disaster. So this event happened 3 years before I was born, and my first true exposure to it was via one of my favourite films, Koyaanisqatsi. Ever since the first time I saw that film back in secondary school in 2001, I'd been fascinated by this disaster. Something as apparently infallible as NASA easily became the victim of its own confidence. Our story today would even lead to a new term, normalised deviance, which probably can be applied to a lot of subjects on this YouTube channel. Right, let's get cracking with a little bit of background. NASA, during the design phase of the Apollo missions, sought out a more cost-effective reusable heavy spacecraft for orbital missions. The concept was decided upon in the early 1970s, and its design was set in March 1972. The design had the orbiter, which housed the crew and payload, with 2 separate reusable solid booster rockets and an external fuel tank. During the mid-1970s, the first orbiter, named Enterprise, was constructed. She couldn't actually go into space, but acted more as a testbed for the systems needed for the project. Eventually, over the coming decades, 6 orbiters will be built, but for today's video we will focus on just one shuttle, Challenger. She was manufactured by Rockwell International, originally being intended as a structural test article to be completed in 1978. After which she was sent to Lockheed for 11 months of vibration tests, designed to simulate entire shuttle flights from launch to landing. We will pause with the Challenger story just briefly to talk about how the orbiter actually gets into space. So, to get into orbit, the orbiter's engines are first to fire up, and a few seconds later the solid booster rockets also start. This is enough to get the spacecraft off the launch pad. After liftoff, the stack goes inverted. The solid rocket boosters and the shuttle with its external tank separate. This is roughly 2 minutes after flight has begun. The solid booster rockets deploy their parachutes, land in the sea, and they are recovered, sent back to land and refurbished for reuse later on. So the orbiter and the external tank continue to ascend, with the orbiter's main engine still firing. The external tank is separated from the orbiter. The external tank, after being jettisoned, disintegrates in the Earth's atmosphere. Okay, so that was a very basic description of how the orbiter gets to orbit. For more information, I'd recommend watching maybe a Curious Droid video. Apparently people think we're related. We're not. So after its mission, the orbiter was designed to re-enter Earth's atmosphere, and upon re-entry, glide to Earth and land much like a conventional aircraft. Well, wasn't that little side tangent exciting? Well, let's get back to the history of the Challenger. It was decided that Challenger should have a new lease of life after her experiments, and was to be converted into a full-blown orbiter. She had her refit for spaceflight beginning in 1979. Many of her parts were sent back to her manufacturers for reworking. She also even had a new fully functional crew module added. The refit took around 3 years, with Challenger rolling off the production line in July 1982. Her first flight was as STS-6, lifting off on the 4th of April 1983. She would take into space over her operating life the first African American, first woman, first Dutch person, and be the first night launch and landing. She was used more often than Columbia between 1983 and 1986, making her the go-to orbiter, amassing 10 flights and over 62 days in orbit. But we'll have to talk about an issue with the shuttle program, and it was around those solid booster rockets, the SRB. Now, those two solid booster rockets were vital to launch, as they provided the most amount of thrust at the beginning. They were built by Morton Firecool. Each one consisted of multiple sections. Each section was constructed in Utah separately to be put together at the Kennedy Space Center, ready for use for blasting an orbiter into the sky. Of course, this requires a joint between the sections, and this came in the form of a tang and cleavage joint. There were 3 in total for each SRB, and they have several vital, especially important for this video, components. So the tang and cleavage joint works like, hang on with me, this is relevant to the disaster, like this. With the tang being the upper segment connecting the two sections by fitting into the lower cleavage section. There is a retaining pin, clip and band placed to hold the two sections together. The joint is also externally wrapped with fiberglass reinforcement tape. To create the seal between the sections, 2 rubber O-ring seals are employed. They run the entire circumference of the SRB, and they are bonded to the case using an adhesive. The seal design was originally considered to be redundant, as if the primary first O-ring failed, then the secondary one could also be relied upon. As such, the seal was rated as critical, but a redundant setup. The gaps between the components were then sealed by zinc putty. The O-ring seals are vital in containing the hot gases produced from the SRB's motors during burning. During operation, they will be compressed, sealing the surface, thus stopping any unwanted flames out of the side of the boosters, which could be a little bit catastrophic. But the system design was flawed. Issues were discovered in the early 1970s. This was that the O-ring wouldn't always compress and would instead extrude. NASA thought this was acceptable, but the issues didn't end there. In 1977, a test discovered that the tang and cleavage joint could bend away from each other. This weakened the compression on the O-ring and thus reduced its seal effectiveness. The out-of-spec situation then allowed combustion gases to erode and damage the seal, causing more gases to escape. The issue was further exacerbated when in lower temperatures, as like with everything, different materials expand and contract at different rates. This greatly concerned NASA engineers, and they requested a redesign of the joint to include a shim to close the gap in 1978. 1 year later, and not having received a response to their 1978 memo, a second one was sent, continuing to object to Firecool's solid rocket motor joint seal design. A test in 1980 showed yet again in a tang clevis relative movement was greater than originally predicted. In May 1980, the Verification Certification Committee recommended that NASA conduct full-scale tests to verify the field joint integrity, including firing motors at a mean bulk propellant temperature range of between 40 and 90 degrees Fahrenheit. NASA replied, NASA specialists have reviewed the field joint design, updated with larger O-rings and thicker shims, and found the safety factors to be adequate for the current design. Reanalysis of the joint with larger O-rings and thicker shims is being accomplished as part of the lightweight case program. The joint has been sufficiently verified with the testing accomplished to date. The first shuttle mission took place on the 12th of April 1981. All went well, but just on the second mission, STS-2, O-ring erosion was noticed, but was found to be an infrequent problem over the coming years. Erosion was found in March and April 1983, and in February and August of 1984, the latter of which had discovered soot had blown past the primary O-ring. Even though after 1982 the O-ring's designation of redundant was removed, and with evidence of blow-by, shuttle launches still continued. NASA would push the design beyond its temperature limits, when in January 1985 the launch of STS-51C being the coldest space shuttle launch to date. The air temperature was 62 degrees Fahrenheit, or 17 degrees Celsius, and it was estimated that the O-ring temperature was 53 degrees Fahrenheit, or 12 degrees Celsius. Surprise, surprise, both SRBs experienced O-ring erosion and blow-by. Moulton-Firecoal determined that the low temperature reduced the elasticity of the O-rings, which in turn resulted in the gap not being fully filled, which would then in turn lead to blow-by of soot and gases. Nearly all of the 1985 launches resulted in O-ring deterioration. This prompted Moulton-Firecoal to redesign the case. However, it was going to take some time, and as such, the original design was to be used till the replacement was available. This would cover the missions that would eventually run into the start of 1986. STS-51L. So I'm not going to go into too much detail about the background of this mission. However, it was quite important in terms of boosting the public's opinion of the shuttle program. The orbiter, Challenger, was mated to her solid rocket boosters and external tank at NASA's Kennedy Space Center in Florida on the 17th of December 1985. The mission had been pushed back to January the 22nd, 1986, after a number of cancellations beginning in July 1985, then due to payload issues in November 85. As such, NASA really wanted to get Challenger into space. She was built and ready to go, and her crew were trained and eager to get on with it. One of the crew of STS-51B was the first participant of the Teacher in Space program, Christa McAuliffe. Again, the mission found itself delayed in January 1986 and was pushed back to the 28th. However, there was an issue. The air temperature was forecast to drop to 18 degrees Fahrenheit, minus 8 degrees Celsius, during the night before the launch date. This would mark a significant drop in lowest temperature the shuttle would ever be launched in. As such, this actually caused some concern with Moulton-Firecoal's engineering team. Blow-by of the vital O-rings had occurred in warmer temperatures after all. A conference call was set up between NASA and Moulton-Firecoal engineers. In the call, Moulton-Firecoal employees Robert Lund, the Vice President of Engineering, and Joe Kilminster, the Vice President of the Space Booster Programs, advocated against launching until the temperature was above 50 degrees Fahrenheit, or 12 degrees Celsius, aka the lowest the shuttle had previously been launched in. But something about the mood had changed in communications between the Marshall Space Center and Moulton-Firecoal. Usually it would be a case that Moulton-Firecoal would have to prove that the SRBs were safe to fly. Understandable in an environment of if in any doubt, don't risk it. However, the Marshall Space Center had moved its position of to prove that the shuttle can't fly, almost as if any doubt was no longer acceptable. Robert Lund would later say, "We had to prove to them that we weren't ready. So we got ourselves in the thought process that we were trying to find some way to prove to them it wouldn't work, and we were unable to do that. We couldn't prove absolutely that the motor wouldn't work." He would also continue to say later on, "Well, that is the kind of mode we got ourselves into that evening. It seems like we have always been in the opposite mode. I should have detected that, but I did not. But the roles had kind of switched." As such, after a 30-minute break in the conference call to confer amongst Moulton-Firecoal staff, management came to the conclusion that flying in lower temperatures should in theory cause no more issues than when the shuttle flew at a temperature of 53 degrees Fahrenheit. When the conference call resumed, Firecoal came back saying that there was substantial margin in the event of failure, and gave their final approval for flight on the 28th of January. Measurements overnight recorded lows on the left SRB of 25 degrees Fahrenheit, or minus 4 degrees Celsius, and the right SRB at 8 degrees Fahrenheit, or minus 13 degrees Celsius. Ice had formed all over the fixed service structure. This caused concern with the orbiter's manufacturer, Rockwell International. They were concerned that ice could damage the orbiter's thermal insulation, However, engineers at Kennedy and Johnson Space Centers advised that there was no issues with the ice. However, an hour delay was ordered to allow the temperature to warm up a little bit. The launch was set for just after 11:30 in the morning of the 28th of January. At 20 minutes before liftoff, ice was seen to be melting and clearance for flight was given for 11:38 am. The air temperature now was around 36 degrees Fahrenheit or 2 degrees Celsius. Time for liftoff. 6 seconds before 11:38 am, Challenger's 3 main engines ignited. At T-0 seconds, the 2 solid rocket boosters ignited and Challenger started to move. Almost immediately, a grey puff of smoke was observed around the right booster's joint near the attachment strut. This was hinted at gas blowby due to the improper sealing of the O-rings. Just 2 seconds later, however, the smoke stopped. This was due to some of the solid fuel falling within the booster and temporarily sealing the gap. At 36 seconds post liftoff, Challenger experienced a severe wind shear. To counteract this, the shuttle attempted to correct its trajectory. The change in yaw and pitch dislodged the solid fuel that had been acting as a plug, and this was at an altitude of 3,000 metres or 9,800 feet. At around T58 seconds, another plume of smoke appeared around the same spots as before, on the right SRB strut. 2 seconds later, the plume begins to touch the external tank. At 64 seconds, a hole could be seen being burned into the tank. This caused a leak of liquid hydrogen fuel. Challenger's computer tried to counter the now lost in thrust from the right SRB. Capcom and the crew aboard the orbiter were still unaware of the unfolding disaster, and at 68 seconds the instruction of throttle up was given. At around 72 seconds, the crew felt a lateral load. Pilot Michael J. Smith was recorded as saying, "Uh-oh." The pressure was falling in the external tank and thus was affecting the main engine's performance. At 73 seconds, the aft dome of the external tank failed, and at around the same point, the right SRB rotated away from the strut. Moments later, the whole vehicle began to break up. The altitude of Challenger was around now at 47,900 feet. The external tank was now fully disintegrating. Challenger was pushed against the airflow and was hit by aerodynamic forces, resulting in a load factor of up to 20 G. The orbiter separated from the external tank and continued to fly for another 30 or so seconds. The shuttle stack had been completely separated, in sections of the now disintegrated orbiter flying about in different directions, hurtling back towards Earth. The crew compartment remained relatively intact. The force at separation was estimated to be between 12 and 20 G, but quickly dropped down to 4 G and then freefall. It could then be seen falling through the sky. The crew cabin fell for approximately 2 minutes and 45 seconds after its separation, eventually slamming into the Atlantic Ocean. At 89 seconds post-launch, the video of Challenger was seen in mission control, and now the full weight of the disaster began to sink in. NASA Public Affairs Officer Steve Nesbitt would announce the explosion when just a few moments before he had been reading out stats from the flight data. He would say, "We have a report of the flight dynamics officer that the vehicle has exploded. The flight director confirms that. We're looking at checking with recovery forces to see what can be done at this point." Recovery operations were dispatched immediately with the ships MV Freedom Star and MV Liberty Star heading towards the crash site. However, due to falling debris, recovery couldn't begin until 12:37. Understandably, hopes were held for any survivors, but with an estimated impact force of the crew compartment with the sea being 200 G, it was very unlikely. By 7 PM, some recovered debris from the orbiter and external tank was found, with surface operations concluding on the 7th of February, subsurface operations ending the next day. However, submarines and submersibles would scour the seabed around the impact area for SRB and crew compartment debris for months to come. Pieces of Challenger would continue to wash up ashore, even as late as 2022, when a pretty large piece of around 20 feet long was discovered off the coast of Florida. The crew compartment would be found on the 7th of March 1986. The remains of the crew were removed on the 4th of April, however one of the bodies floated away. This was Gregory Jarvis. His remains were recovered just over a week later. But what the public really needed to know now was how could such a tragedy happen to NASA of all organisations? Finding the cause. Now I'll say straight away, as this video outline has hinted at, that we know what the cause was. It was the poor decision to launch in cold weather that had reduced the effectiveness of the O-ring seal. But in January 1986, that wasn't exactly obvious. After all, blow-by had occurred several times before, and the orbiter had completed many successful missions. The shuttle had over 2.5 million parts, and it was the world's most complex flying machine. The investigation would be no small task. The Presidential Commission on the Space Shuttle Challenger accident was set up in February 1986, and it was tasked with sifting through thousands of documents, photographs and statements. Although the failing O-rings was a big contender, they did have to look at every potential avenue for disaster. The board included Chairman William P. Rogers, Vice Chairman Neil Armstrong, and then David Acheson, Eugene Covert, Richard Feynman, Robert Holtz, Donald Kutcher, Sally Ride, Robert Rummel, Joseph Sutter, Arthur Walker, Abbott Whelan and Chuck Yeager. The investigation would gain the name the Rogers Commission after its chairman. The committee was split into 4 panels: the Accident Analysis Panel, Development and Production Panel, Pre-Launch Activities Panel, and the Mission Planning and Operations Panel. Each panel will contribute to over 160 total interviews over 35 sessions, and would involve over 6,000 employees from NASA and its main contractors over a period of 4 months. They would zero in via extensive footage of the launch on the cause of the plume of hot gases that appeared on the right SRB next to the strut. The evidence was pretty damning of an instance of blow-by. On the 11th of February, during a televised hearing, board member Richard Feynman produced a sample of SRB O-ring and placed it in a cold glass of water.
Oh, I took the stuff that I got out of your seal and I put it in ice water. And I discovered that when you put some pressure on it for a while and then undo it, it maintains, it doesn't stretch back, it stays the same dimension. In other words, for a few seconds at least, and more seconds than that, there's no resilience in this particular material when it's at a temperature of 32 degrees.
This memorable moment helped solidify in the public's mind of the poor oversight that NASA had demonstrated. Feynman had been at odds with other members of the commission, including its chair Rogers, due to his harsher approach to investigating the evidence. He was much more critical of NASA management and their apparent lack of understanding of the risks that they had taken, with not only the O-rings but other parts of the shuttle program. NASA's standards had seemingly dropped in order to keep up the busy schedule of orbiter missions, which fostered a management culture of quantity over safety, where blatant red flags were ignored. We can see this in Robert Lund's statements after the disaster. I mentioned earlier that he felt the culture had changed from prove safe to prove it won't be safe. Feynman's criticisms and investigation would appear in the report's Appendix F. His conclusions were pretty harsh. Feynman would say, "If a reasonable launch schedule is to be maintained, engineering often can't be done fast enough to keep up with the expectations of originally conservative certification criteria designed to guarantee a very safe vehicle. In these situations, subtly and often with apparently logical arguments, the criteria are altered so that flights may still be certified in time. They therefore fly in a relatively unsafe condition, with a chance of failure of the order of 1%. It was a clear case, as of what sociologist Diane Vaughan would coin, of normalised deviance, which is the normalisation of clearly unsafe practices, exactly what happened with the first case of O-rings blow-by. Just because it didn't cause a disaster doesn't mean it was safe, but NASA and Morton Firecall carried on regardless. The disaster would result in the redesign of the SRB, where the joint tang would have a reduced risk of rotation. NASA also re-evaluated other parts of the shuttle project, which wouldn't have saved the Challenger's crew, but would overall improve safety of future crews in a multitude of different events. And now for the slightly grim part of when did the crew perish. Although the exact moment isn't known, it's likely some survived post-separation, as some switches had been operated but couldn't have been done so by the impact. The crew were failed that day by a culture of safety ignorance. Of course, space travel can't be 100% safe, but Challenger really shouldn't have flown that day. Feynman, in his conclusion to Appendix F, would rather eloquently say, and I think it best describes the situation, for a successful technology, reality must take precedence over public relations, for nature cannot be fooled. Pretty poetic if you ask me. I definitely recommend reading the full Feynman Appendix F section.
Watching, and we'll see you in the next video.